In the past, we looked at the acceleration and velocity and time and displacement of objects that are moving in a horizontal direction. We're going to start looking at those objects moving in a vertical direction or free falling objects today. You can compare the motion directly to a free falling object in a vertical direction with horizontal motion, with one exception. Acceleration in the vertical direction, if you're in the same place on the same planet, are always going to be constant. So what you'll be able to do then is calculate delta x, which is now delta y because it's vertical, using t or time, and a, which is really g when you're looking at free fall for a freely falling object. So an interesting comparison that you can make in a vacuum chamber is an apple falling and a feather falling. They're both in a vacuum, they're both dropped at the same time, and this photo is taken as a time lapse, and the times are 1 second apart. So all of the times are equal here. What you'll notice is that the apple falls slowly at first. The first displacement in the first second isn't very much. The second is larger, the third is larger, the fourth and the fifth are still larger. So you can see that the object is not moving at the same velocity, it's increasing. And as an interesting aside here, the feather that's being dropped falls at the same rate as well. So the mass is not dependent upon, the acceleration is not dependent upon the mass. The feather and the apple, where there's no air resistance in a vacuum, will move at the same acceleration. That acceleration happens to be, if you are on Earth, happens to be 9.81 meters per second squared, and that's free fall acceleration. So it's convenient, you can use that in all of your problems. Looking at another example, which is on page 61 of your book, of an object being thrown from someone's hand upward into the air. As soon as the object leaves a person's hand, there's no longer force from the hand acting on that object. So the only acceleration affecting this object is going to be g, or the acceleration due to gravity. So at first you can see this object is moving very quickly because the acceleration due to gravity has not yet taken effect, but it begins to slow down and it moves slower and slower until finally at the very top we have a velocity of 0 meters per second. The object will then begin to fall, and this fall looks very much like the apple did. It will increase with distance every 1 second. Again, this is a 1 second time lapse. We can compare the picture there to the graph on the right, and if we look at the slope, okay, we have the slope of the object, its velocity versus time as it's moving upward, and its velocity versus time as it's moving downward. So being velocity versus time, this is going to be acceleration. And we see that the only acceleration acting on this object, if you could calculate the slope of this line, you would find that it is 9.81 meters per second squared. And you can give that a try if you would like. At 0, this is where the object's velocity begins to change from positive to negative. So this is the up part with positive velocity, the down part with a negative velocity. And here's the equation that you could use. Now, the equations that you will use here are in the example on page 63. And you can see that it's the same equation, but we're now using delta y to calculate the displacement because we're moving vertical. And those problems that you will do on Friday are on page 64 for problems practice F.